In this video, we're going to find the distance between the point S with coordinates 1, 1, 1 and the line that's given by the following parametric equations. Here my x is given by 1 plus 2t, my y coordinate is given by 2t, and z is equal to 4 minus 3t. As we vary this parameter t, we'll get points along the line whose coordinates are given by these equations x, y, and z. In order to get started in any of these kind of problems, you want to conceptualize things generically first. So in this case, I have some line that I've drawn and some point that I'm presumably assuming is off the line itself. It may actually be on the line, in which case we'll find that the distance from that point to that line is 0, but until we find that out one way or the other, we don't know. So I'll draw it off the line. And I didn't make any attempt to draw these to scale or in reference to any coordinate system. I'm just drawing them abstractly so I can conceptualize what I need to do. So what do we want to find? We want to find this distance that I'm going to call d here from the point to the line itself, and it should form a right angle if I drop down from the point towards the line. What information do I have about the line itself? Well, I know it goes through a particular point. At t equal to 0, it goes through the point 1, 0, and 4 by evaluating at t equal to 0. There is a point on the line. And I know that it runs parallel to this vector v here that's given by the slopes of my linear equations, 2, 2, and minus 3. This is telling me how much I should displace away from the point 1, 0, 4 as I increment my parameter t. I'll increase 2 units along the x direction for each increase in t. I'll increase 2 units along the y direction, and I'll decrease 3 units along the z coordinate for each increase in my parameter t. So it's essentially like a velocity vector of a particle moving along this line. One way I can relate this to other vector operations then now is to draw the vector ps that goes from my point P to the point S. There's an angle between these two vectors which I'm going to label theta. And now I see a right triangle. I can use trigonometry to express the side that I want, the distance here, in terms of the trigonometric ratios involving that angle theta. Because the side that we want here is the opposite side, we're going to need the sine of the angle. So the distance is going to be the length of the hypotenuse, which is the length of the vector ps, times the sine of theta. This looks like a cross product. The cross product of two vectors has the sine of theta when we calculate its length in its length. So in fact, I need to make it look like the cross product, which would be ps times the length of this other vector v forming the angle and sine of theta. Now that's the length of a cross product, but these are no longer equal to each other. So by introducing this extra factor of v, I'm going to have to divide out by that extra factor of the length of v. And now I've made things equal to each other. And indeed, we have the length of the cross product of my two vectors, and I'm dividing by the length of v, which makes sense because the length of v is only, or v itself rather, is only determining the direction along the line, and its length shouldn't be relevant in the calculation. So our final conclusion here is that the distance is the length of the cross product of ps and v, and then we, in some sense, normalize by dividing by the length of v. Let's do the calculations for this particular situation now. ps is the vector from between my 2 points, so I'll need to look at the displacement from that point to this point. So I'm going to subtract corresponding coordinates. 1 minus 1, 1 minus 0, and 1 minus 4. And simplifying that, I get 0, 1, and minus 3. This is a vector, so I've written it in angled brackets to distinguish it from a point. I need the length of this vector, or I need the cross product of ps and v, and we do that by doing a determinant expansion. So I put I, j, and k along the top row, I put ps along the second row, and I put v along the third row. We now expand out the first term, the I component. I look at I, and I cover up the row and column that it is included in, and I look at the little 2 by 2 determinant that is formed there. That's 1 times minus 3, and then minus negative 3 times 2, so it gives me plus 6. When I do the j component, it automatically gets a minus sign. I cover up the row and column that it appears in, and I do the little 2 by 2 determinant, 0 times minus 3, minus negative 3 times 2, so it gives me plus 6 here. And then finally I do the k component, I cross out this row and column, and I take 0 times 2 and minus 1 times 2, and that gives me negative 2. So simplifying, I have the vector 3, minus 6, and minus 2. We need the length of that, and summing up the squares of each component, it's 9 plus 36 plus 4. Take the square root of that, and I get square root of 49, which is 7. We need the length of v itself, this normalizing factor, that's summing up the squares of the vector v, 4, 4, and 9, and taking the square root of that, we get square root of 17. And finally, the distance that we want is their ratio. It's going to be 7 over the square root of 17 units of length, whatever units you happen to be using.